Thank you very much, Bunch. So yes, we had a nice talk earlier in the previous session where Barry Reno from our team laid a nice context for Pine Creek Origins project, the stratigraphy and the geochronology. The last couple of talks have highlighted some of the pegmatite magmatism in the Pine Creek area, and now I want to set the context for the magmatism um, in the region, particularly the felsic magmatism, but also looking at the mafics. And specifically putting it into a tectonic magmatic context. Something that geologists probably don't point out enough, igneous geologists, is that igneous magmatism doesn't happen on its own. There has to be some change in the pressure, temperature, water conditions. Essentially, they are a structural and tectonic product. And that tectonic magmatic framework is what I'm going to discuss today. So the 3 points I really want to be addressing, or at least highlighting, is that these 1.9 to 1.8 GA intrusions are associated with one of the most productive and longest running gold fields in the NT, starting with the 1860 exploration, the mini gold rush of the Pine Creek area, particularly by Chinese explorers. The temporal association of the Pine Creek origin with continental accretion, putting it in the larger context of the Columbia supercontinent. And then what I'm really devoting most of the talk to is highlighting this tectonic magmatic change through the Pine Creek origin, looking primarily at this stage of the project, existing data and early stage geochemistry, and then hopefully as the project evolves over the next few years, or definitely as the project evolves over the next few years, looking more at the isotopes and the geochronology. So Barry laid out the stratigraphy nicely, so I don't need to spend too long on this. I want to highlight that. So we're going to be looking in this talk primarily at these red units. So these are the intrusions that come in, Paleoproterozoic intrusions that intrude shortly after the Paleoproterozoic sedimentary sequence that Barry highlighted earlier. I've overlain on here the boundaries of these three domains, the Litchfield in the west, the central domain, and the Nimbawar in the east, that Barry referred to through his talk, and the mapped gold occurrences from the MODAT database. And you can see this spatial association between known gold occurrences very much strongly associated with this central domain. Is there a tectonic reason for this? Is there something that we can see in the magmatism with which it's associated? Before I go any further, I find it very useful. Australia has a very long history, and it's useful in that to work out where we are in supercontinents. So what's neatly wrapped around Australia is the amalgamation of the Columbia supercontinent, which is expressed in high gravity anomalies and traces of magmatism. So all of these dots on here are a selection of intrusion ages across Australia from 2 to 1.6 billion years. And we can see it forms these nice little lines, largely following these high gravity anomalies. And these are your suture zones through which the amalgamation of the Columbia supercontinent was built. And Pine Creek sits on one of these up in the north. And what I'd like to just highlight is the two other major goldfields of the NT are also pretty much the same age and also associated with these suture zones. But let's look today at Pine Creek and let's look at these. Initially, the felsic intrusions. We'll come to the mafic intrusions at the end. So first of all, are they all coming in at the same time? We've got three domains, so let's broadly through this talk refer to the intrusions geographically where they sit in these three. And we can see straight away, so what we've got here, so we don't have ages for all of the intrusions yet, so we're just looking at the ones that are colored in. And if we take their area, their intrusive area, and these ages from 1875 to 1775, we can see that there's one big pulse, which is largely representing the Litchfield domain in the west and the Nimbawar in the east. That's this large pulse here. And then the central domain is a bit later. It's longer lived, it's not as voluminous. And for a bit of context, referring back to the last talk, the Two Sisters granite up here is part of this first pulse. And those Bino pegmatites and the tiny little Shoebridge granite here, which was referred to in the core lithium talk, that's all the way down here. So quite a separation from the rest of the magnetism. So let's start seeing what we can use the chemistry for. Let's see if we can start to delineate this tectonic setting for these rocks. First of all, let's start with the major elements. Let's go with potassium. So potassium is a good proxy for low degree melts or an enriched source. And straight away, if we take these three domains again, so the central domain on these is the red crosses, and we can see compared to the blue and the yellow for the Nimbois and Litchfield that they're more enriched in the potassium. Are we seeing here some hints towards a different setting or a lower degree? What's nice about potassium is it has a couple of mates, uranium and thorium. They also behave in a very similar way during melting and fractionation, and they also can all be picked out in radiometric surveys. Thorium has a particular advantage, though. If we plot here for samples where we've got analyzed chemistry and radiometric values, and these are the mean radiometric values of these plutons and median radiometric values and median analyzed values for these, we can see that for a given analyzed value of uranium or potassium, that the radiometric signal has dropped off. And that's because in the oxidized regolith on top, those elements become mobile whilst thorium remains immobile. So thorium's a nice proxy to move on from that previous slide. And straight away, when we look at the regional radiometric survey, we can see this high pattern, this high radiometric anomaly in the central domain compared to the absence in the Litchfield and the Nimbois. So we're starting to see some pattern emerging. Overlaying here, these are the median values to highlight that further. And again, going back to that area plot, we can see this peak in this enrichment on the central domain compared to those that precede it. Are we starting to see a shift in tectonic setting? So tectonic settings for granites, for people who've played with granites, they may have come across Julian Pearce's plots. So back in the 80s, it was observed that if you grouped granites from different tectonic settings for specific elements, they would start to cluster. And so you could create patterns between your granitic setting, be it a volcanic arc or within plate granite, relative to in two-dimensional space to certain elements. So for instance, here we've got ytterbium, which is concentrated in amphibole or garnet. So as they fractionate out in conditions with more water or higher pressure, you start to drop your ytterbium. And these are the conditions you would associate with a wet volcanic oxidized arc. And similar with tantalum, which sits in titanite or rutile, again requiring an oxidized system. They will suck out tantalum as you move towards these oxidized volcanic arc systems. And so you can create some idea based on these trace element chemistries what tectonic setting you may be sat in. They're good little tools. And so if we look again, central domain in red, Litchfield and Nimbois in blue and yellow, we can see Litchfield and Nimbois. And I should highlight here, we've got lots of data. If I put it all on here, we'd be in a bit of a cloud. So these are all median values for specific plutons. As we saw earlier, there's a lot of plutons here. We've got a lot of data. So what I'm showing here are median values. This isn't the only data we hold. And we can see that these guys in the west and the east are sitting in the volcanic arc. And we're seeing in that central domain where we saw that higher potassium, a variation from volcanic arc to within plate. So now we get building up more of an idea here that there's a shift going on from that first pulse, the largest pulse of volcanic arc, shifting towards a tendency of extension in the chemistry. And if we use a power law relationship, we can make that more spatial, make it form into a one-dimension space. We can see that concentration in these warm values in the center. So that was good with the chemistry. Something we wanted to see is whether we could find evidence for that in the field. Granites may look very homogeneous, but they host nice features of enclaves. So there's a nice little mafic enclave here, and elongate megacrysts. Plutons away from their margins and away from shear zones tend to express pure shear or record pure shear in their lineations. So if we take here, the red colors on here are your direction of your lineation, and that's your extension direction. Likewise, the inverse of that is your compressional shortening direction. And so if we see here, we've zoomed in a little bit. So there's that Litchfield domain boundary here. Here's the central domain. We see this very strong consistency between these plutons. of an extension towards the northeast-southwest. So now we're starting to get some idea of context. And what's worth pointing out here, northeast-southwest is a good direction, because here's the strike of the strata scattered around. And the dominant, the subvertical strata, northeast-southwest striker, is your dip direction. So we've got a regional compression direction that affected the strata that very closely preceded these intrusions. These are the Burrell Creek particularly, and the Cosmo supergroup that Barry talked about. So northeast-southwest is an extension, it's the inverse of the compression that has folded those sediments. So that's an interesting piece to this puzzle, because then if we go, right, let's see if we've got, when we get some isotope data, we'll have a better way of testing your crustal assimilation. But what we can do already is we can look at aluminium saturation. So to saturate a rock in aluminium you can achieve that through fractionation to a degree by suppressing a plagioclase fractionation. The easiest way is to be melting, assimilating, or clays and micas. And so what we find globally is if you're in a subduction setting, as you move into your thicker crust away from that subduction zone, your aluminium saturation increases. So we get an idea from this that if we move to the west, we've got these very strong colors, these highly periluminous rocks compared to those in the east. We're probably moving away from your subduction system towards the southwest. And based on that extension system we saw in the central, that would put your subduction zone out here and moving inboard towards the southwest. This will be nicely tested when we start getting our isotope data coming. So that seems to be the system we've got there with the plutons. That's moving from an initial pulse arc magmatism that we see in the westernmost, the Litchfield, and the easternmost, the Nimbawa domains, shifting into an extensional, longer-lived system in the center. What about the mafics? So Barry highlighted earlier this shift from Zamu being most of the mafic dikes in the central domain, to this shift between Zamu and Burundi. If you're working in this area, you're most likely going to be working, and you've got some dikes. By the nature of where the national park is, you're most likely going to be working on Burundi. So sorry if that affects what's written in your report. What Barry highlighted is straight away that they look different, the rocks, and this in that the Zamu dolerites looks paler because it's higher feldspar composition, and the chemistry matches that. It's more silicious than the Burundi, so the easternmost are more silicious than those in the west. What about the tectonic setting? And let's include the rest of the mafics here. Let's put this into a broader context. And we can do a similar thing with mafic rocks, as I previously showed with granites, different elements, but we can create tectonic discrimination diagrams. Well, I haven't, but people have, through the same method of looking at groupings of mafics from different systems. And we can do this, and then we can take these plots and we can compare them with the data here. And using the geochronology that existed prior and the new data that Barry showed us earlier, we can see an evolving tectonic setting in the mafics as well as the felsics. So if we start here in the Nimbawa domain in the east, we've got some dikes there that aren't directly dated, but are only associated with Archean rocks. This is this little pink triangle here, and that sits out here on a spectrum from enriched morb. So this is subduction zone mantle, and within the island arc space here. That then, as we move towards the Burundi dolerite, which we now put around 2 billion years, we're looking at an island arc system. And then as we move towards the Zamu and the Maud down here, we start to see a shift towards a continental arc. And what's worth pointing out is these are really good clusters. So it's not just the appearance, the age, and the silica that are differentiating these two groups. Very much the tectonic setting as well that's shifting. As we continue on, we've now developed this continental arc, and then finally the Litchfield. So these mafics out in the west. Look at the green triangles over here. You'll see they plot in the Morb, the island arc, the continental arc, all over the place. And the easiest way to find that, if you wanted to go elsewhere, would be to go and find a marginal basin ophiolite, where essentially the higher the degree of extension, your subduction signature, it can get overwhelmed by higher degrees of extension, and you start to get higher degrees, less oxidized melts, Morb melts filling in. So that's a back arc. The easiest way of doing that, marginal basin, a back arc basin, again tying with that geometry I referred to with the pollutants. And that ties in quite nicely with the previous interpretation by Hollis and Glass. And putting it in our own context, this is a shift from an Archean island arc through to a Proterozoic continental arc as recorded by the mafic rocks, with the back arc in the west, and your felsics recording a shift from a continental arc in that first pulse to more of an extensional system in the central domain. So it looks like there is, in answer to that first question, a tectonic shift between the different domains at different times. So that's where we are at this point in the early stages of our chemistry. Where are we going from here? Well, we're going to be updating and expanding the geochronology. We've already seen some great impacts of that from the work earlier. But also, as we start to really bury into those felsic rocks, can we start to see distinct magmatic and tectonic events? We're going to be collecting whole rock and zircon isotope data. Are we able to see the magmatic sources and the underlying basement? And we're going to be expanding that sample coverage. We've got a lot of fieldwork planned this year to try and expand over units that we haven't sampled and try to test some of these hypotheses. And this leaves us the fundamental questions. What are the nature of those three domains? What is the magmatic tectonic control on this mineralization of this very important area? And as I highlighted earlier, do the Pine Creek magmatic tectonic processes compare with those of the contemporaneous Tanami and Tennant goldfields? Thank you very much.